Hey everybody, welcome back. This is part 2 of a series on the death investigation in forensic science. This video focuses on the time of death. So let's get started. Time of death is the estimation of when the victim died. It's really important when the timeline of the case matters a lot. Example, you find a body in the woods behind some man's house. So you suspect that the man may have killed the victim, but the man has been in jail for the past month. Could they have killed the victim? It depends on how long the person's been dead. If the person's been dead for more than a month, then that means this suspect could have killed the victim before he went to jail. If the victim's only been dead for a couple of days, he couldn't possibly have killed the victim because he was in jail at the time. So there are many cases where the time since death of the body is really, really important in determining the guilt or the innocence of a suspect. Keep this in mind as we go. I'm going to bring it up again and again, but times of death are estimates only, and there are a lot of different confounding factors here that make it really tough to estimate when it was that a person died. All right, so what are the techniques that we have at our disposal for figuring this out? First of all, we have a bunch of techniques that are useful for the short term. So in a window of a few days after death, we can narrow it down a little further, say, this person looks like they've been dead about a day, about 36 hours, and so forth. These techniques are Algar Mortis, so that's looking at the temperature of the body. How cold is it? How warm is it compared to the environment around it? Rigor Mortis, that's the stiffness of the body, the locking of the limbs following death. Liver Mortis, that's the color of the body. We get different pigmentation that occurs as a result of blood settling in different places after a person dies and the heart stops beating. Vitreous humor potassium, so the vitreous humor is the goo in the eye behind the lens. We can extract some of that, measure the amount of potassium ion in that, and make an assessment on time since death. So those are short-term techniques, first couple of days after death. We also have ways of looking at the long-term. So if the body's been there for weeks, months, or even years, we can get a sense of when approximately they may have died. And in the case of long-term estimates, what we're looking at here is decomposition. So how decayed is the body? What are the stages of decay that we're looking at here? And entomology. What bugs are on the body? Where are they in their life cycles? So we're just going to work our way through these techniques, and hopefully by the end of this video, you'll have a decent overview of the different ways that forensic scientists can make estimates of how long a body has been dead. All right, let's start off with Algar Mortis. So Algar Mortis is the process of a body's temperature changing over time. Normal body temperature, for reference, is about 99 degrees Fahrenheit, 37 degrees Celsius. And so the idea is that once a person is dead, their body temperature slowly is going to change to the temperature of the environment. Your body temperature is maintained at 99 or 37 because of activities of your living body. As soon as you're dead, your temperature, like everything else in an environment, is going to slowly match the temperature of that environment. There's a common rule of thumb that you see in forensics textbooks and things like that, that bodies lose 1 to 1.5 degrees per hour Fahrenheit until the body reaches the temperature of the environment. But this is really an oversimplification because there are a ton of factors that affect how quickly a body will shed heat. So it seems strange to have a rule of thumb or a general principle out there when the phenomenon is really quite complex. So I'm telling you about this because it's commonly used, but it seems to me to be sort of a bit of foolishness because there are a lot of factors here. So what sort of factors affect how quickly a body will cool? The temperature of the environment is, if the body is 99 degrees Fahrenheit at the time of death and the environment is 105 degrees, then surely it's not going to be losing 1 to 1.5 degrees per hour. In fact, it'll be warming up. Or if it's extremely cold, then the cooling rate may be much higher than that. The size of the body matters. So a very large body, a very overweight person, or a very tall person is going to lose heat more slowly to the environment than a smaller person. The clothing matters, of course, a lot, right? If a person's wearing a big, thick parka, or if they're in a sleeping bag, then their rate of cooling would be reduced. Is there convection? Meaning, is there a breeze blowing on them? Is there a fan blowing on them? That will cool them faster. Are they wet? What's the humidity out there? These things affect the evaporation rate, and evaporative cooling is a really important mechanism for cooling. So there are a ton of factors here that allow us to, that confound the effort to estimate how long a body has been dead based on its temperature. That said, It's not as though you can't use this at all. If a body is still quite warm and it's a cold room where they've died, then probably they died pretty recently within, the last several hours. So we can use this, but we shouldn't get too excited. Next technique, rigor mortis. So rigor mortis is the rigidity of the muscles. It begins in the first 24 hours after death. The idea is that the muscles contract and they fix the limbs, the fingers, the various muscles of the body in place, in position, often in the position of death. After about 36 hours, this rigidity subsides, the muscles relax, the person relaxes into whatever posture is appropriate due to gravity. Again, how quickly rigor mortis sets in and how quickly it resolves is affected by a lot of factors, which makes it somewhat difficult to definitively predict exactly how old a body is based on the rigor mortis status. So what's the temperature like? If it's hot, then the rigor mortis is going to come on faster, but it'll also disappear faster. If it's cold, then the opposite will be true. What's the muscle mass in the victim? If a person, say, is very elderly, then they may not really experience detectable rigor at all because they don't have enough muscle mass for you to really see them seizing up. Also, what was their physical activity prior to death? If a person died in the midst of hiking or something, then that can actually affect how quickly the rigor comes on and how quickly it dissipates. So rigor mortis is another useful thing. If you see somebody in the throes of rigor mortis, then probably they're within, let's say 6 to 36 hours old, give or take. But even that, it's tough to make the estimate because there are so many factors involved here. Here's an example of a man who died, and you can see his arms fixed in an upward position against gravity. That's the result of rigor mortis. Liver mortis is our next technique. Liver mortis results because after death and the loss of circulation, meaning the heart has stopped, the blood in the circulatory system will settle in the parts of the body that are closest to the ground. So if I'm laying on my back, the blood will settle in the lower half of my body, the back half of my body, if you like, that half of my body. If I'm laying on my side, then it'll settle in the side of my body that's closer to the ground. If I'm standing upright somehow, then the blood will settle in the lower half of my body toward my feet. And what happens is that the areas where the blood has settled take on this purplish, reddish color. This happens in somewhere between 20 minutes, 3 hours, of course, affected by a lot of different factors, but relatively soon after death. And then after, again, roughly 16 hours, the color is fixed. So the blood sort of clots in place, and after this point, it's not really going to change, it's not really going to go away. Now, how do you know whether it's fixed or not? You can actually press on the body, and if the color disappears because the blood has moved out, when you press on it, we call this blanching, then we're still in the early stages of liver mortis. If you press and there's no blanching, it stays red, then you're in the later stages of liver mortis and it's already become permanent, so usually after 16 hours. One of the interesting things you can deduce, other than just the time of death, based on the liver mortis or the lividity patterns, is maybe you'll find a body where the lividity patterns indicate that they died and were laying on their right side, and yet you find them laying on their left side. What does this suggest? It suggests that the body was moved sometime after they died, and that might be an important part of the case. Why would the person be moved? Maybe somebody was trying to cover something up or make it look like something it wasn't. Suspicious. Worth looking into. So that's liver mortis. And again, there are a lot of factors involved, but the timelines, again, depend on temperature. Really important factor for all of these is temperature. So here's an image depicting liver mortis. This person, it looks like, died on their back, and blood settled into the skin of their back. You see, there's a lot of whiteness on the mid-upper part of their back and around the belt line, and then it's cut off in this picture, but toward the buttocks as well. So why don't we see liver in these areas? Those areas were probably under pressure as they were laying there. So probably the back was resting on the mid-upper portion of the back, and the rest of their weight was supported by the buttocks. And then it looks as though they had a tight enough belt or waistband, something like that, to prevent liver mortis from occurring around the waistline. So there's an image of liver mortis in a deceased person. Next topic, vitreous humor potassium concentration. So It turns out that after a person dies, the cells within the inner surface of the eye start to release potassium ions into the fluid of the main compartment of the eye. That's the vitreous humor. We'll look at a picture of this in just a moment. And so as a result of this release of potassium ions, the concentration increases over time, and you can measure it. So what we would do is we would extract from the eye with a needle some of the vitreous humor and measure the potassium. And the more potassium we find, the older the body is, the longer it's been there. And this is relatively consistent within the first 48 hours after death, beyond which it's not really a useful technique. And that's true for all the ones we've looked at so far. They're really only useful for the first 3 or so days, after which point you can't really rely on them. So here's an image of the eye, and what you can see over on the right side here is the cornea. The cornea is the outer surface of the eye, so if you were to poke yourself straight in the eye, you'd be poking yourself in the cornea. Behind the cornea, you have the lens. This is the bit that changes its shape to help you focus on near or distant objects, and then the muscles that surround the lens that help it to contract and expand so you can focus on things. And then here we have in the main cavity of the eye, this is the vitreous humor. So this is the stuff that you'd have to extract in order to check the potassium concentration. How do they do it? They poke a needle in through the side of the eye to extract the vitreous humor. I found some pretty grisly pictures of needles poking into eyes. I decided to spare you. But if you're interested, you can Google vitrectomy and, see needles in eyes to your heart's content. So that's the idea. We pull the vitreous humor out, some of the vitreous humor, we assess the amount of potassium is in there, and we can use that again to estimate how long the person's been dead. Here's a chart, actually. On the x-axis, you can see time since death in hours, and on the y-axis, you can see the potassium concentration in millimolar. And you can see there is a clear trend here that over time, the amount of potassium ions in the vitreous humor increases. So if we find somebody that's got a potassium concentration of, say, 11 millimolar, we trace that over here, then we're looking at somebody probably who's been dead somewhere between 20 and 30 hours-ish. You can see there's a lot of variation in this chart, so even now it's still an estimate, but there's something to it. There is a real relationship here. As always, things like temperature, other factors do affect this measurement as well. Moving on. Decomposition. So it's past the first couple of days. The body is really starting to fall apart now. These stages of decomposition are what we can look at in order to figure out how long the body has been there when it's much older than a few days. So decomposition is the process by which the body separates into its components and its structure, both large scale and small, disappears. So we stop seeing, really nice organs with all their beautiful structure and their tubes connecting to the right places and all those sorts of things. That all falls apart. The formerly beautiful person that's died turns into something I think most would consider something a little less than beautiful, and so forth. From a certain perspective, decomposition is a really horrible, grisly thing where all that is beautiful turns noxious and decayed. From another point of view, decomposition is a really wonderful, beautiful thing by which the components of the body return to nature and become once again a part of the circle of life. So it sort of depends on your perspective. No matter what you think, it's a little tough to look at sometimes, and the smell is not great either. So the stage of decomposition is what we're looking here. The stage of decomposition can be used to estimate the age of the body, but again, universal caveat for time of death, there are a lot of factors that affect the rate of decomposition. So stages for decomposition, there's 2 stages. The first one we call autolysis. This is the first stage. It's when digestive enzymes inside of the cells are released from the places where they're normally stored, and they then proceed to actually digest the cells where they were stored in, and the surrounding tissues as well. So digestive enzymes in your pancreas, for example, that are normally used to digest food, are busting out of their normal role and actually digesting your bodily tissues. This rate of digestion varies from organ to organ, so the pancreas probably digests itself a lot faster on average than, say, the muscle tissue or the kidneys. So it varies from organ to organ, but you can get a sense of how long a person's been there by how far progressed the autolysis process is. After autolysis, we have putrefaction. This is the next stage of decomposition. These overlap, by the way. They're not mutually exclusive. It's not like the bacteria in putrefaction are going to wait until autolysis is done before they really go to town. But generally speaking, autolysis is the earlier process, and putrefaction is the one that goes on for a long time afterward. So this is digestion and consumption of the body by bacteria. These are bacteria that were on your skin. These are bacteria that were out in nature that you happen to bump up against. These are also the bacteria that are in your gut and helping to keep you alive right now. Right now, they're helping you digest your food, synthesize vitamins, coordinate your immune system response, all kinds of really important roles without which you'd be in big trouble. When you die, they're going to take advantage and have a feast. Putrefaction is accompanied by the production of gas, which leads to the bloating of a body. The bodies can become so bloated that eventually they burst. This is the stage when we get foul smells, unusual colors in the body. It's not unusual that a body is discovered because somebody smells that sickly sweet odor of death and knows that something's wrong. This process of putrefaction will continue as long as conditions are good for the bacteria until there's really nothing left but the skeleton. So what I'd like to take a look at now is a time-lapse video of the decomposition of a pig. And this will give you a sense of what the process looks like and the different stages involved in the process over the first week or two. So let's take a look at that, and then we'll come right back. Welcome back. So there you have it, decomposition, time-lapse. What you probably noticed in that video is that there were a lot of insects involved crawling around, chewing on this little piggy. So entomology is a really important part of estimating the time of death. So in nature, if you've got a body out there exposed to the elements, insects are going to detect that, they're going to smell it, they're going to find their way there, and they're going to have a feast. They're going to either directly eat or they're going to lay their eggs and their little children will eat the body. So it turns out that these bugs show up in relatively predictable waves. So we usually see blowflies first, and then we'll see maybe ants, and then later on we'd see perhaps spiders that just happen to wander on. They're not eating the body, but they just happen to wander on and so forth. So we can tell something about how old the body is just by looking at what insects are present on it. We can also determine something about the time since death by looking at the maturity of the insects that are on the body, because we actually know a lot about the life cycles of some of these insects, how long it takes them to go through different stages of their lives, and so we can say, that bug is there at this stage of its life. Well, it takes 10 days to get to that stage, which means this body's been out here at least 10 days. So we can do some work like that. So we can estimate it based on what insects are present and how mature they are. Again, this is the refrain I hope you're expecting. This depends on the weather, it depends on the temperature, it depends on the time of year, the species of insects that are around in this environment, the compounds in the body. So, right, if a person's on certain pharmaceutical drugs, the bugs may not find them quite as appetizing and the process may slow down. There's a lot of factors, as always. So here is the bug that is most commonly used for this type of thing. It's called a blowfly, in this case the green bottlefly. And if you will draw your attention to the lower right hand corner, you can see here is the point where the adult lays eggs. Then within about a day, it hatches into a larva. This is what we call a maggot. After about another day, the larva is now in its second stage. After another day, it's a third stage, bigger and bigger. Right? So if we saw just eggs on the body, that would mean this person's probably been dead for a day or less. If we see only really small maggots, then we're talking about 2 days or 1 day. If we see the medium-sized maggots, then we're talking 2-3 days. Larger maggots, 3-4 days. And then if we see pupas, then we're looking at maybe like a week, week and a half. And then if we see a second generation of adults, now we're looking at 2-3 weeks and so forth. So by assessing what stage of life these blowflies are at, we can estimate again how long the body's been out there and how long these bugs have been making a snack out of it. So that's entomology. Now, I have said it several times already, but I want to really emphasize this because whenever we're doing forensic science, it's really important that we understand the limitations of the work. You may be a forensic scientist someday, or you may be in a courtroom where a forensic scientist is testifying. And if a forensic scientist ever gets up there and says, we know definitively that this person died 37 hours ago, and 37 hours ago the suspect was in a position to have killed them, and therefore the suspect killed them, you should know well enough that that's nonsense, that they can't pin it down that precisely. Maybe it's possible that it was in that ballpark, but you really can't pin it down quite that well. So you should be knowledgeable here, especially if you ever end up on a jury, and talk to the other people on the jury so that they understand that these things are not quite as definitive as testifying scientists always make it out to be. It's not to say that they're trying to lie or deceive you always or something like that, but people sometimes put a little more confidence in the work that they do than perhaps they ought to. Okay, so we've looked at short-term technologies for assessing time of death. We've looked at Algar Mortis, the temperature of the body. We've looked at rigor mortis, the stiffness of the body. We've looked at livor mortis, the color of the body. We looked at the vitreous humor potassium in the eye. We also looked at decomposition, process of autolysis or self-digestion, the process of putrefaction, digestion by bacteria, and we also looked at the entomology, what bugs show up and what their life cycle can tell us about how long a body's been out there. Now I'd like to conclude with a little story. So this happened in the 1950s in Denmark, and some farmers were out in the peat bog near their farm, cutting up some peat. Peat is a fibrous plant material, like a moss, and folks will dig it up and burn it for fuel. Great fuel source. And as they're digging in the peat bog, getting the peat to burn in their furnace, they find a body, and they think, this body's relatively fresh. It looks like someone's been murdered recently. They call the police come out, they go, oh yeah, they start an investigation into this person's murder. But they look at the body and it looks a little strange. I mean, it does look relatively fresh. Actually, here's an image of it. So here's an image of the person they found. And they see, he looks like he's in pretty decent shape, right? You can make out all the features of the face. You can even see stubble on his chin and on his lip. You can see his hair and everything, right? So he doesn't look like he's been there for a really long time. At the same time, he's sort of leathery. So what are they thinking? Maybe a couple of weeks, a couple of months, maybe a year? They call in an archaeologist, or an anthropologist rather, a forensic anthropologist. They do some testing. They find out that this body has been in this bog since the year 400 BC. This body, in other words, is over 2,000 years old. So the initial estimation of this body was off by over 2,000 years. So this just goes to show that you've got to be careful when you're estimating time of death. All right, I think that's it for today. I hope you found this enjoyable and educational. I hope it helps, and we'll see you next time. Bye for now.